All right. Well, I'm Sam Narriman, one of the organizers. We don't have name tags, so please introduce yourself to each other. And we're going to have 3 mini courses. The first one is by Professor Takashi Tsuboi. We're actually very happy that Takashi made here to Purdue. He's one of the foundational figures in foliation theory. The professor at the University of Tokyo and now professor at the University of Tohoku, telling us about Godbillon-Vey and piecewise linear homeomorphisms.
Okay, thank you very much for the kind introduction. First of all, I thank organizers Hyun-Kyu Kim and Yash Lodka and Sam Nariman for the support, really generous support for me to come to here. And I'm honored to give you some talk on the things I did something like 35 years ago, maybe. Yes. So I'm talking about the Godbillon-Vey invariant and piecewise linear foliations. Did I this? Oh, and the group of the piecewise linear homeomorphisms. All right. So it's maybe not necessary, but I have been at the University of Tokyo, in fact, for 41 years. When the first I got the job in 78. And then I lived there, so 7 years ago. And for these 2 years, I'm working at the Tohoku University, Sendai, Japan. And then the Godbillon-Vey invariant was the main theme of the research around, say, 1980s. And then the problem was, so you can define the Godbillon-Vey invariant. Oh, I should have no. You put?
Yes.
Oh, good. Oh, very good. So the Godbillon-Vey invariant, Godbillon, was found in 1970 by Godbillon and Vey, and it is a characteristic class for the foliations. And then until that time, all the characteristic classes we know was either the Chern class or Pontryagin class, and it related to the manifolds. And there is a very strong theorem on the classification of manifold, the cobordism theory, that said essentially, if these invariant are 0, the Chern classes and Stiefel-Huytony classes and Pontryagin classes are 0, then it is cobordant to 0. Cobordant to 0 means the manifold itself is a boundary of the n plus 1 dimensional manifold. And because of the Stokes theorem, and these characteristic classes are represented by closed form, so if it is a boundary, it is 0. The one way is easy, but the other way is very difficult. So if you have something which has the invariant 0, then it is a boundary of something. It needs a construction, and it was the main theme of the mathematics or the topology, differential topology of 1960s, I think. And then after that, this Godbillon-Vey invariant was defined for codimension 1, first codimension 1 foliation of the 3 manifold. Maybe transversely oriented if you need. And then the same question arises. That means we want to know. So whether, so if it the, oh no, sorry, MF, so the manifold with the codimension 1 foliation is the boundary of the, so maybe this is 3 now, it is codimension 1, and then form, and some G, and boundary of this O equal to M, and then the G is transverse to the boundary, and G restricted to the boundary is F. Then I have not yet defined this invariant, but it is defined by closed form, so it is evident that the Godbillon-Vey of the M3F equal to 0. And what I wanted to know is not this direction, is that whether it is possible to show something like this. And then, so there is work by Thurston, in fact, just after the discovery of this invariant, that Godbillon-Vey invariant has the, you can deform the foliation, and then the invariant varies continuously and non-trivially. So it has a value on the all the reals. So that is the very different feature than the old characteristic classes. And the, as I said, for the manifold, we have good characterization of the cobordism class of manifold by the characteristic classes. But that characteristic classes are something discrete value. So you can think about only countably many manifold and countably many invariants. So the question was, if it is 0, then whether it is cobordant or not. Then there are many, not so many, but people worked rather hard to know whether it is possible to do something like this. And some, after that, I would like to change the question, so I say the direction here, it is not really necessary that it is cobordant, the boundary of something. I mean, so if there is MF is a kind of limit of the MIFY, and then MIFY, if the invariant is 0, and then I didn't say much about the Godbillon-Vey invariant, but so as I said, it varies continuously, means if you vary the foliation, this invariant varies. So, oh, sorry. No. This one and MIFY boundary of WI, GI, sorry. So if it is the limit of null-cobordant foliations, then the Godbillon-Vey invariant just I erased, but it is 0. And as it varies continuously, Godbillon-Vey of MF is 0. So it is a little weaker condition that makes this invariant 0. And for that, it will be better to think about this question. All right? So if you have some manifold with a codimension foliation with the invariant 0, and I try to find manifold and foliation which approximate that foliation. And if those foliations are all the boundary, then I think in some sense the converse is true. And then, so the relation to the conference today is I want to take this piecewise linear foliations one can take these are the piecewise linear foliations, and then at that time, so 35 years ago, there is already the theorem by Greenberg. So you can say a lot of things on the piecewise linear foliations. So the B gamma PL but is in fact known to be BR delta BR delta, and this is joint. So once you have piecewise linear foliation, Greenberg says it is in some sense, defines a 3-cycle in the B gamma bar PL. This is the classifying space for the piecewise linear foliations. And the homotopy type we know. And this we know, and also we know the generators of H3.
Greenberg's only for codimension 1? Is his theory only for codimension 1? Or does he even
Yeah, to this clarity, I think so. I mean, he has a paper with the foliation by singularities. Singularity in this case means the non-differentiable points. And then it is not really depend on whether it is codimension 1 or not. But for the piecewise linear case, so something like this, if you have a holonomy like that, then this is only defined by the slope of the holonomy. And the slope of the holonomy is the element, the logarithm of the slope of the holonomy is the element of this. In fact, I should write R plus, but if you take the log, this is BR delta. So that's why we can really determine that. I think codimension is higher. You can write, in some sense, similar thing, but you don't know about how is this classifying space of the local group, I mean. Yeah. And then what I said is we know this H3 P gamma bar PL is generated by PL lab foliations. I think you can imagine more or less what is the piecewise linear lab foliation. First of all, you have to know what is the lab foliation. So the lab foliation, this is S3 with the lab foliation is the union of D2 cross S1 lab component of, say, some number A and B. Okay. So this is called lab component, and lab component is as a figure you will see I think that should appear in the poster. Should it? No. No. It is so two-dimensional lab component is something like that. And three-dimensional lab component is you will take the center circle and you turn around this center circle to get D2 cross S1. And this alpha A is you will have the holonomy here. And we will assume that this holonomy is linear. And log of the holonomy line is this A. Is it clear for you? So another way to define is you will look at the R2 cross R plus. This is so the like a half space, and you have foliation of this space minus 0. So I include this is 0 and infinity, and R2 cross R plus is the upper half space, and then I foliate it by the hemispheres, and then these hemispheres. And we divide it by the homoscedasty. So something like e to the a. So e to the a means the, of course, you will put some hemisphere, the larger hemisphere of this homosthetic action. Okay, so this small means bigger and much bigger because it is exponential. And then if you divide it, you have this space. And holonomy should be something which appears. And then if you calculate it, it is e to the a. And this is the piecewise linear Leb component. And this is another Leb component. And if you glue two solid tori, then you will get S3.
How do you know that's not
How?
How do you know that's not bored to 0?
Because of the discrete Godbillon-Vey invariant.
So it's not, there's no obvious reason why it's not bored.
No. Yeah. This is part, so I'll say Ghys Sergiescu Godbillon-Vey invariant of this S3R is in fact AB. So this is the reason. And this is also the cobordism invariant. So if A and B, usually A and B are not 0, and then it is non-trivial.
But what if one of them is 0 and the other wasn't? Would it be bored?
0 means it is, if you divide this one by 1.
Oh.
So,
Singular.
yeah. Mm-hmm. So as I said, I wanted to do something on the characterization of the Godbillon-Vey invariant by means of the null-cobordant foliations. And then if we can use the piecewise linear foliation, then we can use the result of the Greenberg and also the Ghys and Sergiescu, or Dumi and Sergiescu, maybe. There is invariant, like Godbillon-Vey, and it gives a B. And in some sense, if you have piecewise linear foliations, it will define some 3 cycle in the classifying space. And by the Greenberg theorem, it is cobordant of the plenty of the piecewise Lev foliations. And the sum of all the Godbillon-Vey numbers is 0. So this is the situation. And so you will see what is necessary to do. And first, first question, and in fact, we thought first of all, maybe I should say classical Godbillon-Vey invariant, and Sergiescu Godbillon-Vey invariant, or that is discrete. Godbillon-Vey invariant for piecewise linear foliations. These should be different because much before this Godbillon-Vey invariant for the smooth foliation, we look for if 2 foliations are topologically equivalent or C1 equivalent. And then we ask whether it is the invariant is the same or not. Okay? But as I said, for the piecewise linear Lev foliations, the value can vary itself. All of these things are topologically the same. So first we think this one and this one should be different. Natural, I think. And then there is also, I should say, Hurder, Katok, Godbillon-Vey invariant. And this was defined for C1 plus alpha foliations, and alpha is I should, yeah. You can do better, I know. But so for safety, if this is C1 and alpha Hurder, the derivative is alpha Hurder. And then if the alpha is greater than 1/2, then also you can define the Godbillon-Vey invariant for the foliations. And it is also the cobordism invariant. And this one and this one are not topological invariant. Yeah. So for this, it is not topological invariant. And then for the very good example for that type of the foliation is the stable foliation or unstable foliation of geodesic flows on surface, negatively curved surfaces.
By topological invariant, they are homeomorphic.
There are two foliations. There is a homeomorphism sending all the leaves to the other, and this invariant can be different. In other words, we want you to show if you have such a homeomorphism, the invariant should be the same. But we couldn't because it was false. We tried a lot, in fact, but
That would not stop AI.
what?
That would not stop AI.
Yeah. And then so I don't say a lot about this stable foliation or unstable foliation. This is the, so you have a negatively curved surface, and then you look at the unit circle bundle, maybe U sigma 2. And then here is the geodesic flow, and the leaves are all the union of the geodesics, which has the same limit behavior. So if the two orbits at the infinity will be moving the same, then these points are all on the same leaf. And then it was in fact Mitsumatsu who found first there is something strange. And then if it is negatively curved with a curvature -1, this is a very good foliation, very, very beautiful foliation. It's how do you say, defined by the action on the Lie group. But once it is negatively curved but not constant, then the leaves are not C2, and in some sense Hurder and Katok show that leaves are C1 plus Zygmunt. So if, even if it is not constant, the curvature is not constant, still the leaves of the stable foliation or unstable foliation defines. So this foliation, I should say, foliations. Leaves are C infinity, but foliations are not. The transversely, it is C1 plus Zygmunt. And then C1 plus Zygmunt is in fact included in all one alpha 1. Anyway. And then it is of course greater than half, and it has the Godbillon-Vey invariant, and this varies, in fact, as we vary the curvature, and in fact, the minimum is attained by the constant negative curvature. So there are these two, at least, at that time. And then it was, I think, it was necessary. So it is not real theorem, but there should be natural domain of definition of Godbillon-Vey invariant. It's a kind of faith. So that should include these two. And then I first worked on these things. Yeah. So the stable and unstable foliations are foliations of the circle bundle, which is transverse to the fiber. And then it is in some sense very natural to think about foliated S1 product or R product. This is some easy thing. It is some so foliated S1 product is a foliation on some today two surface times circle, and then F is transverse to the circle direction. So F is transverse to fibers of projection. And this is the same. And then this structure is, of course, described by the holonomy diffeomorphism. By 1 of the sigma G to this case diff of the circle or diff of a real line. And essentially, we look at the diffeomorphisms preserving the orientation of the circle, or diffeomorphism with support compact, the compact support of the real line. Because if you want to integrate something, then the support should be compact so that the integral converge. Okay. So if you have this type of foliations, then so this one is foliation on the 3 manifold, codimension 1 foliation of the 3 manifold, and this is also, and also the out of the compact part, the foliation is trivial. And then we will see that Godbillon-Vey invariant of the yeah, is the diff of the circle, maybe to. So if we want to calculate for such foliations, then you have say this, and then foliation is some field here, transverse to the fibers, and then you will take a base point, and you will take the generator of the pi 1, something like this. And then this will give you the holonomy homomorphism, that is from the pi 1 of the surface to the group of diffeomorphism. And then, in fact, for this, this will give you, as you know, you have anyway you will get take some triangulation with one vertex of the surface, and for each edge so this one is A, B, B, and so on, okay? And maybe C, C, D. So as you know, this pi 1 of this one is A, B, C, D equal to 1, defined by this commutator relation. And then you see this one is BA, this one is is it? Okay, A, B, A inverse. And then this one is the commutator. Oh, I got inverse, but anyway. B inverse, A inverse, B, A, like that. So this has 6 triangles with the name of the holonomy each side, and you will use this kind of if it is F and G. Then the 2 chain on the group of the on some group is attributing some number on this. I will call this F and G. So if you give this value GV of FG in R, which is a cocycle, to be a 2 cocycle, and explicitly GV is area of log of F prime G and log of G prime. So cocycle can be deformed by adding some coboundary. So it is not only the way, but if you define this one, then it will give this Godbillon-Vey cocycle, and which for this foliation gives the value of the Godbillon-Vey invariant. Is it clear?
So what does it mean? That's an area of 2 functions?
I'll give you. Yes. Hope, no. 5. So what is the area? So area of the 2 functions on circle is the, if you have 5 psi in the, say, C1 of the circle, and area of 5 psi is the, if you look at the image of 5 psi, then it will somehow, from the base point of the circle, you will follow the value here. Okay? So these are the function of the circle. So the function on the circle, the pair of the function from the circle, it is the, you will have image of the circle to the 5 psi. This will give you some closed curve. And for this closed curve, you can define algebraic area. And in this case, it is just phi d psi. And okay. Yeah. And then the area has some good property that area is bilinear. That means area of phi 1, phi 2 side equal to area of phi 1 and of course if you want to put some number, you can put it is bilinear and antisymmetric. This is not important, but and what is good for the area is C1 parameterization invariant. That means area, if there I have a diffeomorphism, and then area of the phi of f psi of f equal to area so it is, I think, clear that if you it will give you the same curve even if the parameter is changed. You may think that why I said C1 it looks C0. I think it's true for this, but later there is something different. And then one thing very good is, I think, remarked by Hurder. Area is defined for C1 alpha, alpha greater than 1/2. So a kind of easy guess given by Hurder is you look at this integral. This is C1 plus alpha. This is no, sorry. This is C alpha. If phi it is C alpha, it is alpha minus 1. Unfortunately, alpha minus 1 is negative. But if you multiply these two, then it recovers C2 alpha minus 1, and it is 2 alpha minus 1 is bigger than 0. And it is true. True means you have this area. So with this Hurder Katok Godbillon-Vey invariant is the area of log of f prime g and log of g prime. Okay. So the other interesting thing is how about piecewise linear? For the piecewise linear foliated product that should exist, and then the holonomy is piecewise linear. But if f and g are piecewise linear of the circle, then log of f prime, say, and log of g prime so each function is something, if you have S1 parameter and the value, piecewise linear map is, as you know, something like this. Then, for example, this has value always 0, and something negative and constant, and again 0, and something positive, and again 0. So these are step functions. So it is something like this. And this one is also. And then if you look at the image on the on the plane, you will see something like that. Because they have only finitely many values. Okay, but you know that the circle has a cyclic order, and you know from one value at some point, and you know at some the non-differentiable point, it will move to some other point. And also, this will move to some other point, move to some other point, move to some other point, and returns. So you see the polygon, and polygon has a algebraic area. So you can define with this polygon the area, and this will give you also area is the Sergiescu Godbillon-Vey invariant for f and g. Godbillon-Vey cocycle.
There was an old paper of somebody called Gelfand and Fuchs and somebody. Didn't they define a Godbillon-Vey for PL?
Gelfand.
Yeah, wasn't there an old paper? Not Lewis and McKeown. I'm wondering if that's the same as the Sergiescu.
Yeah, maybe. Yeah, their definition is, yeah, just a little different. And then, yeah, we will look at that later. I cannot respond immediately. Okay. So maybe it's time. I stop here today. Thank you.
More questions?
This same thing as Bot Thurston, this slide?
Yes. Yes.
And a question. In the case of the rank foliation, in the smooth setting, is this cobordant?
In the smooth foliation with the Godbillon-Vey invariant is 0. And also it is cobordant. It is resolved by Sergiescu. Yes. Yeah, it was the first very good, interesting question. And then, yeah.
An example cannot be made PL in general.
So at that time, so Sergiescu's paper was, I think, in 76, and piecewise, Gelfand piecewise foliation, piecewise linear foliation was already appeared, but in this setting, so Greenberg's work is about 90. Yeah, so we didn't think about that. In fact, if you calculate the Godbillon-Vey form, and you will find, if the holonomy is linear, you will find a kind of residue along the, for example, compact leaf. And we wondered why it is. But after that, we understand much better thinking about this piecewise linear or Greenberg's foliation with singular leaves. Yes.
All right. If there's no more questions, thank Takashi again.
Thank you.